Now let's take a look at the transfer functions using the SR model for the MOSFET and see how that changes our analysis. Okay, let's see if that changes whether inverters that are built out of these MOSFETs, when we use the more accurate model for the MOSFET, let's see whether they still satisfy the static discipline under the more accurate MOSFET models. So let's start with the model for our MOSFET inverter. And notice here that I've shown you the basic schematic of our MOSFET inverter with a switch. And when I replace that with a MOSFET, I'm going to get a MOSFET in place of the switch here. Now, under the conditions that I use to get different inputs, so for C equals 0 and for C equals 1, I get different subcircuits. So for the MOSFET in the off state, here is the circuit that I get. Okay, so this is RL, this is VS, this is my output V out. I get C equals 0 applied to the gate of the MOSFET, and this is for the condition that VGS is less than VT. And the MOSFET is in its off state, and the switch is the MOSFET switch is turned off. Then for C is equal to 1, I get a slightly different situation. I get something that looks like this. So this was R on. In this situation, I get RL and VS as before. Here's my V out. But here, C is equal to 1, and VGS is greater than or equal to VT. And in this case, this is R on. And notice that the MOSFET switch in this case is going to be in its on state. That's the basic circuit that I'm going to get. To make it very clear, let me just draw a line here so you can see the two circuits clearly for the on state and for the off state. And as before, I can write the truth table for the MOSFET. None of that changes. So this is the output of the device. Let me call that the logical output OUT, and V out corresponds to the voltage. So out corresponds to logical output, and the voltage is V out. So as before, nothing really changes when C is a 0. In this case, on the top diagram, I get V out equals 5 volts, so the output is a 1. And when C is equal to a 1, then something interesting happens. So when C is equal to a 1, what is V out? So when C is a 1, V out can be written as follows. V out is a voltage divider action between RL and R on. So I get VS is R on divided by RL plus R on. Okay, so that is my V out. So really just by looking at it, I actually cannot say whether the output is going to be a 1 or a 0. But let's make the assumption that R on is much smaller than RL. And if R on is much smaller than RL, then I can make this expression here much less than VOL. I can make it less than VOL. Okay, so if R on is much less than RL, then I can ignore R on compared to RL, and so R on divided by RL is going to be significantly lower than 1, and multiplied by VS, I can make that less than VOL. So if I end up choosing my parameters, in this case my parameters are RL and R on and VS, if I choose these parameters, RL, R on and VS wisely, then I can make this condition to be true. Okay, I can make sure that V out is less than equal to VOL for the case where C is equal to a 1. So in that case, when C is a 1, I can get a logical 0, a correct logical 0 at the output. And so this is the key expression, which is VS R on divided by RL plus R on must be less than equal to VOL, and that will end up giving me a valid output when the input is in a high state. I can now plot the transfer function for the inverter using the more accurate model, the SR model for the MOSFET. I've shown you all of these things before, so I won't redraw them for you. So I show you the inverter up here, and then I show you the sub-circuit for the inverter when C is 0, and sub-circuit when C is a 1. When C is a 0, notice that the switch is in its off state, and when the sub-circuit is, when the input is a 1, the MOSFET is in its on state, and the second circuit applies. So I can now look at the various values and see what the voltage transfer function really looks like. And to do the plot, let me make the assumption that RL divided by R on is 10. Okay, I'm going to pick my MOSFET such that RL divided by R on equals 10. Now, in general, you can go look at your textbook, and the textbook will talk about how you can design MOSFETs to have various values of R on. The basic way is, just as you make an element wider, if you increase the width of an element, its resistance decreases, so you can make the MOSFET wider, and that reduces its resistance. So the book will show you how to do this. It's not that important for 6002X. So RL divided by R on equals 10 for in my little example. I'm going to pick Vs equals 10. And so therefore, my expression for Vs R on divided by RL plus R on, which was the low output voltage, is going to be 0.45 volts. So R on is, if RL divided by R on is 10, then this expression becomes Vs times 1 divided by RL divided by R on plus 1. Okay, so if RL divided by R on is 10, then it's Vs divided by 11. And if Vs is 10 volts, then Vs divided by 11 is 0.45. All right, so let's take a look at what the voltage transfer curve for this inverter looks like under the more accurate model for the MOSFET. So when Vin is less than Vt, the switch is turned off, and so the output is straight Vs. Okay, so the output is straight Vs when Vin is less than Vt. Okay, no surprises there. However, when the input C equals 1, in other words, when Vin is a high value, then the MOSFET turns on, and Vout is given by the voltage divider action between R on and RL, and specifically, the output is going to look like this expression here, which I found to be 0.45. Okay, so this is my function here. So this is 0.45 volts. So this is the transfer function. Recall in the past, when I had an ideal switch, my output was along the x-axis, but in this case, it's translated up to 0.45 volts. So this is the transfer function of a MOSFET under the SR model for the given choices of Vs, R on, and RL. The next question to ask ourselves is, does this inverter still satisfy some of the voltage thresholds we looked at previously for the same voltage thresholds of various static disciplines? We'll just do one example here. You can try out the other examples yourself, but let's do this example here. And I've shown you the voltage transfer function on the left-hand side for the inverter with the SR model for the MOSFET. So just to be clear, let me just write that down. So this is using the SR model for MOSFET. Basically, I get the low output voltage at 0.5 volts. And so the question then to ask ourselves is, does this satisfy the static discipline? So notice, as before, most of the things stay the same. The transition point is at Vt equals 1 volt. So as was our usual trick, let me draw the horizontal and vertical lines. So let me start with the VOH and VOL lines. So VOL is at 0.5 volts, and then I'm going to draw VOH at 4.5 volts, and then I'm going to draw VIH at 4.1, and then I can draw VIL at 0.9 volts. So notice that according to what I described to you earlier, the valid regions are here, and notice that when the input is less than 0.9 volts, the output is in the valid region, and when the input is above 4.1 volts, the output is again in the valid region. So therefore, this inverter does satisfy the static discipline for even under the SR model for our choice of RL and R on. Okay, notice that the 0.45 appeared for Vs equals 5 volts and RL divided by R on equals 10. And in fact, you may want to play around and see what would happen if the following were true. So what would happen if you chose R on RL divided by R on to be a different value? Okay, so let's say we chose RL divided by R on to be 5. Okay, instead of 10, we chose 5. Okay, I'd like you to go and think about whether you would still satisfy this static discipline under the condition that RL divided by R on is equal to 5. So you should go ahead and try it out yourselves and convince yourselves whether this inverter satisfies the discipline or not under this new choice of RL versus RON.